All right, everybody. So we're back here. We're going to do some graphing. We're first going to graph 3 to the x. And I'm going to start by choosing some x values to plug into x. So these are my x values. And so f of x is going to give me some output values. When I plug, let's start with 0. When I plug 0 into here, 3 to the 0 is 1. And since anything to the 0 power is 1, the 0.10 happens a lot on these graphs. I think I can zoom in a little bit here. And let's go to the right here. When I plug in 1, 3 to the 1 is just 3. So we get 3. And when I plug in 2, I get 3 squared, which is 9. When I plug in negative 1, this is 1/3, so that's that negative exponent rule. And when I plug in negative 2, I get 1/9. Okay, so you can see that just moving 2 to the left here, I'm at 1/9, which is really hard to even graph here to get 1/9 accurately on this. The thickness of my pencil almost makes it too close to the x-axis. 1/3 is about right there. Okay, and then we go up. We already have 0, 1 on there, but then we go up to 3, and then by 2 we're already up to 9. So we've gone very quickly from very small numbers to very big numbers in the span of 4 x values. And so what we can see is, if we think about what's happening here, as I move further to the left, like if I plug negative 10 into here, 3 to the 10th is, maybe my calculator is 59,049. So when I'm here, this is really 1 over 59,049, which if I do 1 divided by that number, it's 0.000017. And so 0.000017 is really close to 0. And I wouldn't even be able to graph it here. So as I move further to the left on this graph, these numbers are getting closer and closer to the x-axis, but they're never actually going to hit the x-axis because this is not 0, but it's close. And if you think about it, no matter how big of a negative number I plug in, negative a billion, 3 to a billion is a number, and 1 divided by that is really close to 0, but it's not 0. And so this is that idea of an asymptote that we talked about back with our rational functions. So this is like a horizontal asymptote happening, and it's the asymptote itself is this x-axis, but we're going to get really close to it, but we're never really going to touch it. I know the thickness of my pen sort of makes it look like we're touching it, and if you graph it on your calculator, it's going to look like it's also touching the x-axis on your calculator. But this is the basic shape of our exponential function. And because 3 is bigger than 1, this is why we get this growth, okay? We start small over here at negative infinity, and we end huge. Now this is only 2 and a little bit over to the right. If I kept going to infinity or so on and so forth, this graph blows up really fast. But it keeps going. Okay, so over here, there at 8, there is a point on the graph. It's just way up there. Okay, so that's exponential growth. All right. So now let's graph 1/2 to the x. So when I graph 1/2 to the x, I'm going to use the same values, the same x values, negative 2, negative 1, 0, 1, and 2. And y is going to give me some values. Let's start with 0 again. 1/2 to the 0 is 1. When I plug 1 into x, I'm going to get 1/2. So this is already a fraction, 1/2. And so now when I raise it to a power, 1/2 squared is 1/2 times 1/2, which is 1/4. It's smaller. So now when I raise 1/2 our base to a larger exponent, the output's going to get smaller as I move to the right. But when I plug negative 1 in, what that tells me to do is it tells me to take the reciprocal of the base and raise it to that exponent. And so I get a larger number, 2. And when I plug in negative 2, that gives me the reciprocal raised to the positive 2, which is 4. And so now as I'm moving to the left, you can see our numbers are getting bigger. And so when I plug in negative 1, I get 2. When I plug in negative 2, I get 4. When I plug in negative 3, I would get 8. And then when I plug in 0, I get 1, and then I get a half, and then a quarter, and then an eighth, and then a 16th, and a 32nd, and again, I can't, it gets so small so quick, it's hard to even draw it without looking like I'm on the x-axis itself. Okay. And so we still have this horizontal asymptote at y equals 0 when I graph this. But this is considered exponential decay because the base is between 0 and 1. The base can't be negative, so it's either going to be between 0 and 1, or it's going to be bigger than 1. It can't be 1 either, because 1 raised to the x is just 1 everywhere. And that's just a horizontal line. That's not very interesting. It's not exponential. So let's say, since we know that all exponential functions are some base raised to an exponent, and then you can have some constant multiple out in front, we can find, if we know that the function that we're looking at is exponential, we can find the equation of it, and all we need is 2 points on the graph. The first point is going to help us find the base, and the second point is going to help us find the C value. Okay, so when I plug in negative 1, 18, I'm going to get C times a to the negative 1 equals 18, which means that C divided by a equals 18. Okay. When I plug in 4, C times a to the 4th is equal to 2 over 27. Okay. Now all I'm going to do is a simple substitution here, because I can say that if C divided by A is 18, that means C equals 18A. So I can replace this C value here with an 18A times the A to the 4th that's already there. Oops, I said A, but I wrote 8. A to the 4, and that's going to equal 2 over 27. Now A times A to the 4th is A to the 5th using our exponent rules. This is 2 over 27. So then we have, I can divide both sides by 18. 27 times 18 is 486. So A to the 5th equals 2 over 486, which I can reduce to 1 over 243. And now if I want to get A totally by itself, I'm going to 5th root both sides. So let me just rewrite this equation. I'm going to take the 5th root of both sides of the equation. Another way to do this would be, if I want to get rid of the exponent 5, I could raise both sides to the 1/5 power, which is the same thing as the 5th root. But if you want to think about it like this, this is a little bit easier to put in your calculator. So I get A equals, and I can put 1 over 243 in my calculator and raise it to the 1/5 power. I can actually put the fraction in, and it gives me 0.3333, but I know that what my calculator is really trying to tell me is 1/3. Okay, and on your calculator you can hit math. Fraction is the first option, math frac, and it will take your previous answer and turn it into a fraction, which in this case it turns it into 1/3. So I have my A value. A is 1/3. So now that means that my function is f of x equals c times 1/3 to the x power. Now I need to figure out what c is. Well, I can go ahead and use this original equation here that I got. C equals 18a. So c is equal to 18 times 1/3, which is just 6. So my actual function is f of x equals 6 times 1/3 to the x. And this is my final answer here, is this equation. Okay, so a lot happened there. If you want to stop the video, go back and rewatch that, I recommend you do so. Alright, I will see you in the next video when we talk about solving using some of our exponent rules.